Okay.
Okay,
Um,
let's go.
okay. Well, we've reached that point where we kind of exit the galaxy and deal with things that are similar phenomena, but not on a stellar scale. So, in trying to pull everything together, since we started with accretion disks and then went to symbiotics and ionized structures that were being driven by radiative and hydrodynamic processes, and then went to H2 regions and extended structures and looking at the differences between those and active structures like supernova remnants. We kind of bring it together here with the recognition that there are ob objects and systems in the universe that spectroscopically uh, display a lot of the characteristics of things we've been talking about, and yet do so on a scale that is incomparably larger, and consequently on timescales that are significantly different. And why I want to emphasize through all of this as a kind of bringing together of everything that we've been doing, which is why I wrote how everything we've done comes together, is that the thing that unites all of the cosmic environments is that all of the physical laws are the same. They change their manifested action only because the scale is different. But at the basic level, we don't have that many processes that we have to worry about. What we have to understand is the way that they combine and behave in different settings. So to use the example of an H2 region, because we're going to keep coming back to that, in ordinary interstellar settings, which means molecular clouds and diffuse gas, when you put a hot star in place, and in this case, you know what the word hot means, that it's not just the spectral energy distribution, but it's actually a statement about the physical constitution of the star. And that star is irradiating this background with a radiation field with a spectral energy distribution that is sufficiently hard that it can ionize the background. That's taking place in a medium whose structure comes from something else than the star. When we talk about H2 regions, those are very big structures in which the stars may be born and that they may stir up. But for the most part, these are regions that are affected only by the radiation from the star. And consequently, what you see depends on two things, one of which is very remote from the other. The source of the radiation is different than the manifestation of that radiation as it's converted in the background. I don't mean this to be sounding technical. It's just a very important point that everything we're going to be talking about is the ultimate example of non-local. And non-local in the sense that the radiation source has nothing to do with a major part of the region that is showing up spectroscopically and also photometrically. So to begin, um, when we talk about active galactic nuclei, this is a term that goes back to the 1970s and 80s. Active was thought to mean unusual in that galactic nuclei were originally, as they were conceived of in the Hubble Atlas and, oh, probably in most elementary textbooks, they're kind of dull, boring places where the stars are old and kind of trapped inside some potential. Maybe there's a bar, maybe there's a bulge, but yeah, kind of who cares? It's just a part of the galaxy. Until it was realized in the 1950s and then in the 60s that something was very weird in the centers of many galaxies, when it was finally understood that radio radio stars, as they were called in the late 1950s, the ones that showed up in the first interferometric surveys, like the third Cambridge, those were actually not stars at all, but some of them were actually associated with objects that appeared to be galaxies. Uh, it wasn't clear what. Then it became much clearer, first in the 1960s and then later in the 70s and 80s, that there actually was something unified. And the thing that brought it together was actually spectroscopy. So we'll come back to this slide. I just wanted to start with this so you have a list of the species, the beasts we're going to be talking about. They have, in many cases, absurd names like liners, which does not mean that it has lines. It means that it's a low ionization, but low ionization has a very specific meaning. Narrow and broad have very specific meaning. Blazars and quasars are in many ways related, and we'll come back to that. So, um, techniques we're going to talk about that I really want to emphasize are spectropolarimetry, which turns out to be far more important for these than first had been realized in the very earliest days of the work, became obvious in the early 1980s as a genuine skeleton key for understanding what the interior structures of these objects is. But ultimately, it's become possible to do this kind of work in 2 dimensions and spectroscopically, instead of simply taking filter images, with the advent of specific instruments on the VLT and eventually on ELT, and presumably on some of the other uh, someday to come online telescopes. What made all of the difference was not the radio emission. This turned out to be not a red herring. It was a proper indicator of something weird going on. But much more to the point, these turned up in X-ray sources. And there, the epoch of X-ray observations of active galaxies really begins in the 90s with Chandra, and in the 80s with the Einstein Observatory. The general discovery that when you had active galactic, when you had the indicators of something weird in the center of a galaxy, it also showed X-rays. And as the line that I've used before from Ghostbusters goes, you do not expect that kind of behavior from a major appliance. Um, Strong X-ray emission concentrated in the galactic center is genuinely strange. You might expect that you could see extended diffuse X-ray emission because you had supernova remnants or something like that, but that wasn't what you were seeing. And finally, the current epoch, the thing that has made high energy astrophysicists salivate, was the continuing observations with Fermi, with the Cherenkov telescopes, of emission from MEV to above TeV. This is actually a clue, a fundamental indication of what's going on. But as I'll try to come back to during our discussion, uh, it's not as strongly indicative of everything you would ever want to know about these objects as it's been presented. Uh, it's it is extremely important, but everything you see on this slide has similar importance. And to build the integrated picture, we're going to have to start from scratch. Okay? I hope this is making sense. Um, so, um, excuse me, let's go back to this. Okay, so the history. Um, where this all starts is actually this paper, Seifert, 1943. You might ask, how the hell is it possible that somebody could be publishing something about spectra of galaxies in the middle of the Second World War? But Seifert happened to have been involved in observations at, well, he was involved in spectroscopy. He was at Vanderbilt at the time in a situation in which astronomers were involved in other ways in the war effort. What you see here is both the abstract, which begins with the statement, apparent relative intensities of the emission lines of 6 spirals were reduced to true relative intensities. The observed intensities of the emission lines exhibit large variations from nebula to nebula. Now, realize that by this point, these were well understood to be external galaxies, okay? All of the targets that were included here were in the among the brightest galaxies known, specifically all of the stronger emission lines from 3727 to 6731 found in planetaries like NGC 7027, which is one of the standards in the galaxy, appear in the spectra of the 2 brightest spirals observed, NGC 1068 and NGC 4151. And then comes the kicker. Profiles of the emission lines show that all the lines are broadened, presumably, important statement, presumably by Doppler motion, by amounts varying from 8,500 kilometers per second for the total width of the hydrogen lines in NGC 3516 and 7469. The hydrogen lines in 4151 have relatively narrow cores with wide wings. Again, important, 7,500 kilometers per second in total width. And then he goes on to talk about the fact that the rest of the galaxy spectrum, which was also showing up on his data, looks ordinary. So it's basically a stellar spectrum. But these were objects that were specifically chosen because there was something peculiar about them. That is, they had bright, almost stellar nuclei. And there was no other reason for taking these spectra. It was simply the anomaly that structurally, within the bulge, you could see that there was something distinctly concentrated. To make you feel better as observers, you can take a look at these profiles and realize that these had to be done by hand, that they were done with microscope tracing and estimates of the intensities using a calibration wedge. Seifert's observations were following a comment actually by Slipher, and it's the same Slipher who kind of anticipated Hubble in realizing, well, didn't anticipate everything about Hubble, but anticipated the observation that there were galaxies that had displaced velocities greater than what you would expect from orbital motion within the galaxy. Before World War I, Slipher had already called attention to the anomalous structure of NGC 1068 and 4151, and that these had weird appearance, even though in the period before the war, he had no idea that these were external galaxies. Okay, the reason that the reason for the comparison with NGC 7027 is that planetary nebulae are in fact the standard, not H2 regions, for extreme spectra, in the sense that their densities are low enough that you got all the forbidden lines that you would want. The central sources are hard enough so that you have high ionization states. You normally, for example, don't see strong O3 from most H2 regions. And you certainly don't see things like iron 6 or 7. Okay? But you do from planetary nebulae because the central source is sufficiently hard. And that was something that was apparently involved here. We then jump, amazingly, more than a decade to 1958, this paper by Vulture. The comparison between this paper and Seifert, I want to emphasize, is truly amazing. That out of nowhere, Vulture, following the literature, this is the same one who, hanging around Chicago, had known all of those who were working on galaxy dynamics, including the Burbages, and Prendergast, and Chandrasekhar, and Strömgren, and all of those names that you know from the history of 20th century astronomy. Vulture was a theoretician, but recognized that what was happening here was something that wasn't simply Doppler. This was Doppler indicating something dynamical that could actually be used. That if you're looking at an ordinary galaxy, let me emphasize this, it doesn't matter what the galactic potential looks like. You're not going to see orbital motions around galactic centers, even in the interior, with velocities of more than a couple of 100 kilometers per second. And in the galactic centers themselves, you would expect, if you had a homogeneous distribution, the same thing that you would if you fell through the Earth. You know that when you're in the center of a spherical distribution of mass, there's no net gravitational force. Okay? So you would expect that if you are in the interior of the bulge of the galaxy, there's very little mass inside you as you go progressively closer to the dynamical center of the galaxy. And instead, there was this thing sitting in the center that was producing the lines that Seifert saw. And what was more to the point, by this point, there was a distance scale. So it was possible to say that these galaxies weren't simply point-like, that you knew what 1 arc second corresponded to at a distance of NGC 4151 or any of these others. And that's the part that's so important in Vulture's statement, that what he says in the abstract is a mass of a few times 10 to the 8th solar masses is needed to prevent the disintegration of the source. Okay? That was also connected with magnetic fields. So it was that the nuclei are extremely narrow, of order 100 parsecs, and if a normal mass to light ratio applies, extremely massive. The width of the emission lines, which indicates velocities of a few thousand kilometers per second, is probably due to fast motion, circular or random, in the gravitational field of the nuclei. The high stellar density in the nucleus may provide a source of excitation. And that led to the 1960s and the explosion of everything that we now know about active galactic nuclei. This is the point at which it gets defined, that the central object within the inner 100 parsecs has a mass incomparably large compared with what you would expect for a nuclear cluster. In the 60s, this was shown to be actually unstable, that if you could get that much mass in that small a region, the equations, I'm sorry, I don't want to say it that way, the physics of strong gravitation, effectively general relativity, would say that the tidal effects, the warping of space-time, would become so strong that these would actually collapse into some central object that now we would call a supermassive black hole. But the idea was you couldn't maintain, as the resolution became better. Here it was 100 parsecs. When you got it down to something like a parsec, And the mass interior to that was found, as it was for several of these galaxies, to be above 10 to the 7 solar masses. That's unstable. You literally can't build a cluster that will remain gravitationally bound and not collapse in on itself. So this was the indication that something would be happening in these centers if the amount of emission was really indicative of the mass. The next thing was, sorry, here. Where is it? Come on, here. Okay. Can you see this now?
Yes.
Okay, 3C273, a star-like object with large redshift. Reading this, first of all, you see the whole length of this paper, okay? This is the announcement of the discovery of the quasars. That's the whole paper. And there's a second paper by Oak on 3C273 that talks about the energy distribution. And there's another paper about 3C48 by Greenstein that says, oh, by the way, this one also has a ridiculous redshift. The spectrum you see over here that, you know, this is where 4861 is supposed to be. This is where it is. That is, this is shifted from this being like 3,800 angstroms to almost H alpha. And the O3, that is the emission line of O3, okay? The forbidden nebular line is shifted along with the Balmer series, okay? This indicated a redshift of order 1/10. This had never even been dreamed of. And this is in a source whose name indicates that it's a radio source. This is not a star, it's a bloody galaxy. And if that redshift, when people finally got reasonable and realized that this was genuinely cosmological and not gravitational, when it was realized that this was part of the cosmic expansion, with the change in the Hubble constant that had already occurred, it was still too high, but leaving that aside, this indicated that you were looking at a cosmologically distant object whose emission in radio and in the optical was strong enough to detect from Earth. It indicated luminosities from the central object of roughly, to put it in relative terms, the entire galactic luminosity from a region with a volume of a couple of cubic parsecs. That was what became the basis of a long-standing controversy of contrarians for at least a decade that wasted an awful lot of time, but ultimately was resolved by a single paper, and that's the one I want to go to here. This paper by Kachikian and Wiedemann. This was resolved, people, by spectroscopy. It was realized that the quasars and the Seyfert galaxies have the same damn spectrum. They're just different redshifts. And this is the paper that I think defines what we mean by an active galaxy. That what was realized was two things. First, there were objects that became known as Seyfert galaxies. That was more honorific than realistic. Wiedemann needed, okay, these were galaxies that had, in many cases, turned up as strong ultraviolet sources in a survey from Burkhan that had been done by Markarian. This was an objective prism survey analogous to the HD survey and analogous to the Tonnentzintler which had been done by Harrow in the 60s. It was a wide field survey looking at all of the strong UV sources. UV in this case, meaning from about 3,700 angstroms up. It involved using special prisms, and it was very low resolution, so the nature of the objects was kind of mixed. But the point was, these were frequently then followed up in spectroscopy and turned out to show the spectra of Seyfert galaxies as they had been defined by Seyfert. Within this, two classes were identified, so-called Seyfert 1 and 2, and that's what I'm going to be concentrating on now. Those that show broad lines for the permitted lines and narrow lines for the forbidden lines, hence the term broad line and narrow line region. And that's why I said this brings together much of what we've talked about. The broad line, you can guess, I don't have to, I don't have to stretch this out as some kind of mystery story, is from some kind of an accretion phenomenon in the immediate vicinity of the central engine. Now, I'm not specifying this yet as something like a supermassive black hole. Let's just say you got something bloody massive, bloody compact, and surrounded by garbage. That garbage is certainly not going to just fall directly in because it's in a galaxy. And so there's going to be some net angular momentum, and ultimately that's going to form an accretion disk. However that disk emits, it's got to be similar to that which we see in Novian cataclysmics and mass exchanging binaries and mergers and everything else we've talked about. That's a region that's dense. And so one wouldn't expect in that region that you would see emission from gas requiring densities lower than about 10 to the 6th or 7 per cubic centimeter. In other words, when Seyfert compared the lines that were present to those of a planetary nebula, that was very important because it meant that all of the narrow lines, which he specified to be the norm, were all the ones that you see in planetaries. And you know that that means a hard source and low density in the environment, but higher density than you normally have in an H2 region. Okay? Now, the narrow lines were all systematically present for all of the transitions, but the broad lines were found in this list only for the permitted transitions, which means recombination. Again, you got to remember that collisional excitation and de-excitation of hydrogen and helium lines is something you might have in a stellar wind. You might have it in ejecta from mergers. You are not going to have this in the interstellar medium. It's entirely photon processes. So this was indicating that there were regions which had to be physically distinct from each other because the narrow line region, which showed the forbidden lines, was only at most a few hundred kilometers per second, which would be consistent with galactic motions, with expected dynamics from simply orbiting within a galaxy. So this could be a very extended structure. There was no restriction. The narrow lines, on the other hand, would be from a region that was surrounding what would be the broad line region, because you could see that among them being optically thin, it's very hard to surround an optically thin region with an optically thick region in terms of densities. It's hard to construct that kind of density distribution. So it was pretty much thought already, as soon as this paper had been published, that you could distinguish two classes. One, the Seyfert type 1, that is broad permitted, narrow forbidden, and Seyfert 2s, which were narrow permitted, not as narrow, of course, and narrow forbidden, which frequently showed the same structure of the lines in the sense that the ionization was similar, but something was weird about the dynamics, such that the region that was forming the permitted lines somehow was truncated or restructured, or you were seeing some different orientation. That was still not well understood, even into the 1980s. What was most important, though, in our discussion is that the quasars were type 1. That when you had a spectrum like 3C273, and you saw it on the comparison with the normal spectrum, the emission lines appeared to show the indications of an active galactic nucleus, which meant that okay. If you can wait for just one moment, okay?
Yeah.
Um, okay, um,
Thank you.
so my apologies. The importance then was that this also cleared up something about the quasars, that those who thought that these things were somehow extraordinary objects that couldn't possibly be outside the galaxy, and there was a school of thought that actually said that, were immediately quashed, because now you could identify these as simply being so bright that you couldn't actually see the fuzz of the galaxy in which they were embedded. Okay? And from that point on, everything that I had listed as the categories, that is, these, was now available. That is, starbursts were defined as indications of intense star-forming activity, which means these are objects that do not have high ionization present from accretion onto a compact object. These are simply regions that look like 30 Doradus on steroids, or Orion pumped up, that these are essentially stellar continua, which is extremely important because stellar continua are not anywhere near as hard as you would expect from the accretion onto a compact object. You simply cannot reach that emission in the ultraviolet or the far ultraviolet, because the hydrogen is still going to be sufficiently neutral, and then the helium will be sufficiently neutral that you're going to get cutoffs, where if you have accretion onto a central object, the material may be so highly ionized that you literally have no ionization edges. And it's just thermal continuum, thermal bremsstrahlung. So the starbursts turned out to have all of the emission line characteristics, except for the very high excitation, and velocities that were hundreds of kilometers per second, that indicated that you were stirring this thing up, which is the other thing that happens when you start forming massive stars. You have lots of supernovae and winds, and the indications were that these were also compact. They were concentrated in the nuclei of galaxies, at least the ones that were being sought. The one who found this particular phenomenon, Vicky Bolzano, happened also to have been one of Weidmann's students. So it was kind of connected with this spectroscopic tool to distinguish these objects. The low ionization nuclear emission line regions are basically the same thing, that these are indications of some kind of nuclear activity, but not necessarily accretion onto a compact object, where the broad narrow line radial galaxies can be nothing else. That the only reason they are radial galaxies is for non-thermal processes, and low ionization are actually indications of thermal processes. The Seyferts have an intermediate group, which was identified by taxonomically characterized by Osterbrock. And again, it's because of the continuum between these different types in going from the type 1, which clearly indicate two regions, to type 2s, which look more like they're, yeah, maybe one region. And then there's this group called the blazars, or the BLAC objects, which are strong radio sources, strong gamma sources, very strong X-ray sources, and most importantly, they are virtually featureless spectroscopically, which is why many of the people who work on them love them, because they don't have to actually think about physical processes when you can do just photometry. And that's about the only insult I'm going to make in this entire discussion. Um, Now, as an example, these are, let me see if I can, okay, so here, this is what's meant by a type 2 Seifert. I just wanted to show one good example. 5728 is one that is actually pretty for a lot of reasons. It's very much like NGC 1068, which is the poster child of type 2s. You notice first it's a barred spiral. It's an HST image, by the way. It's an active star-forming galaxy, and there are, aside from the stars, you can see that in this composite, there's a ring of star formation, there's a central bar, you can see the dust lanes. It's everything you would expect from a galaxy, except that you look at the center and bingo, it's saturated. And that's what has the spectrum up here. That this is a prototypical type 2. This is an HST spectrum where you see that it has what looks like a nebular spectrum, except the line widths are not nebular. But what's most interesting about this galaxy is what I wanted to show on the right. This is a relatively new paper. This is what you can now do with Muse, among other. This is integral field spectroscopy, where you can look at specific lines and map them out and actually do it in velocity. So what you're getting is either you're getting fibers that are covering densely a region. So it's the equivalent of taking, depending on the aperture of the telescope you're working with, you're taking the equivalent of a bundle of spectra, that all of this is covered by a set of fibers, each one of which is producing a high resolution spectrum, high enough in this case that you can actually separate them on velocity channels. And because it's an integral spectrum, you get the whole spectrum. This isn't photometry. You can choose how you combine those in such a way that you can eventually reconstruct the actual distribution of those lines. And this is what I wanted you to see, that the central object here is one that has different excitations, that the center has the spectrum of an AGN, and this portion in the periphery has the spectrum of an H2 region, and the green are these low ionization, which means sort of dense regions, and the whole thing is extended, and it's extended in the direction perpendicular to the bar, which is actually the same thing as in 1068. But this is the sort of thing that you can now do. We can't because none of us have 8-meter telescopes in the backyard with integral field spectrographs attached to them, but people do. So you can actually get the spectra for yourselves once the data becomes public, or you can just marvel at what comes out. Uh, the thing that's most important is that this spectrum is the integral of this. Okay? So in this, one of the things that's used for separating out the different excitation modes is to use these different line ratios to identify pixel by pixel what's going on. And here, the thing that you see is that the region which we call the narrow line region is an extended structure and extended beyond the central nuclear emission. This is actually, to me, the most interesting thing that came out of this paper, that this is the location of the centroid of the emission, depending on which tracer you're using. And this region is in arc seconds, so you're dealing with something here that's the equivalent of the inner galaxy in our case. That when we talk about the inner or central molecular zone, we usually mean something within 100 parsecs or less. And here, the individual centers, depending on what tracer you're using. So the silicon 6, for example, is very, very close to the AGN location, okay? But it's actually rather far from the forbidden iron 2. So there's this extended region that we would call the narrow line region, and then there's the central AGN, and you can actually separate these out. Okay, this is the other example, which is M87. This is a set of VLA plus VLBI images. They're taken at different wavelengths. So 20 centimeters is relatively low energy. And all of these, and that's the reason I'm showing this, all of these are the indication that activity implies non-thermal. None of this gas at these frequencies is thermal radiation. This is from synchrotron, which means two things. First, there's got to be a magnetic field. The field can be weak, but you've got to have spiraling electrons. And second, those electrons have to be damned energetic. They have to be of order gigavolts. And now to put that in perspective, that means these are ratios of 1,000 times the rest mass. So these are extremely relativistic electrons that have been accelerated to extremely high energies, energies that normally one would expect to have in laboratory settings only under accelerator conditions, that can not only propagate, but propagate to distances. So to make this clear, we're talking here about regions, when we look at this large region, of something like 1/10 of a parsec, okay? In this inner region where the source is, and going to something of order 100 kiloparsecs when we get to the largest scale diffuse structures. Okay, and the integrity of the jet, the integrity of this outflow, maintains itself in going through the interstellar medium of this and other galaxies without disruption. So this is an electron beam of the Star Wars sort that manages to literally burn through the interstellar medium of this galaxy without being completely disrupted. And the only way that that can happen is if you can accelerate it from a central object. And this is why specifically M87 as the brightest galaxy in the Virgo cluster and the central galaxy was chosen as the target for the Event Horizon telescope. So this is why M87 was the one chosen for the first appearance of a black hole. But we know that the central object here is extremely massive because there were HST observations in the 90s that showed the emission lines from the narrow line region around this central object had velocities at parsec scale of 1,000 kilometers per second. Okay, so this is a radio galaxy. This is another class of radio galaxies. That is, these come in two varieties. You've got to love astronomical taxonomy, right? That if you have three objects, you divide them into two categories. Okay, these were divided because there appears to be a difference, a fundamental difference in structure that happens at a particular energy for the radio emission at 20 centimeters. That it's a convenient frequency because that's where most radio telescopes are most efficient. That's also where the 21 centimeter line is and the hydroxyl maser. And there are a lot of reasons why that was chosen. The difference is 10 to the 26th watts, that those that are more intense were found by Fanaroff and Riley when the galaxies could actually be resolved with the VLA to show this sort of ghostly structure. That is, you have a jet and an extended lobe in which it appears, and I have to emphasize, appears is the word here, because there's no dynamics visible here. On a scale, I should make this clear, of 100 kiloparsecs. Okay, so at the speed of light, you're going to have to wait. The inner region, you can see changes on, for the inner region, you can see changes on timescales of actually minutes in extremely high energy to years if you're working on the inner couple of parsecs with radio observations. You can't hear. So the inference is that this jet, which is characteristic of these sources, makes it in integral structure to a distance of 100 kiloparsecs and then slams into or is decelerated from this background because it finally has literally run out of steam and creates these hotspots, which are the impact sites within the lobes. These are called Fanaroff-Riley or FR2. The others are less energetic, where, like this one, which is another interesting case because this is bent back by its motion relative to the cluster in which it's located. This is embedded in a background gas, which sweeps this jet back, but still does not disrupt it. Looking at two different frequencies, you see the same structure, but it isn't just a resolution effect. The lower frequency is actually fuzzier. But this you can see here in the center, a kind of, let me see if I can blow that up. Okay, here, that this is what's meant by a Fanaroff-Riley 1. It's a relatively low energy, low luminosity galaxy, which in moving through this background has a contrail. But this contrail is synchrotron radiation. So these are electrons which have been injected from the central object and are traveling out. This is what's meant by an active radio galaxy. Okay? So I hope that puts it a little bit better in perspective. So now, just for contrast, I wanted to show this. I never do this kind of political discussion with you guys, but I think it's kind of worth it that the the Weidman Kachakian paper is here in time. That when it came out, you can see that it made a difference, and then it kind of just simmered out as something that you occasionally referenced. Okay, and um, this is to show Seifert's paper. So what I wanted you to notice is that before the mid 60s, nobody gave a damn that the paper was sitting there for 20 years before anybody realized that, oh, by the way, this was really important. So I would like you to take this also as an object lesson that when you get interested in something, pursue it and don't think about whether it's going to make a splash or not. The splash may be 100 years from now when somebody has the intelligence to go back into the literature. But this is also something to emphasize. Whatever you get interested in, go back into the astronomical literature and figure out what the context is. Understand, know the papers. You can do that until this administration does something stupid like cutting the ADS because of removing NASA funding or closing the CFA. As long as that stuff is available, and it will be mirrored somewhere, the literature is available. You have no excuse for not indulging your curiosity.
You said no politics, Steve?
I, yep, perdonami.
No problem, of course.
Okay, so um, this is the UV, and that's really important because in quasars, this is what we see in the optical. Okay, so to connect and really understand what's going on, you have to take the galaxies that you can resolve well and look at them in a multi-wavelength fashion. And I'm deliberately using IUE data because this is about as close to what you will see without B and with low resolution spectrographs as anything that I can show you. This is a resolution of 1,000. So you can see this, people, if you take a spectrum of 3C273, and you can do that with a CCD and ALTB and patience on a reasonable backyard telescope. This is what you're going to see, except it's going to be in the optical instead of at IUE wavelengths of below 2,000 angstroms. Okay, this is carbon. This is carbon-4, helium-2, the silicon-4, oxygen-4 lines, and this is Lyman alpha plus nitrogen-5. This narrow line is the thing that gives this away. That narrow line is the emission from scattered light in the Earth's geocorona. That's scattered sunlight at Lyman alpha. So that tells you what the resolution of this data is, because that's just the filled aperture. Okay? And this is Farrell 9, which is also a type 1 Seifert. And this one happens to have a narrow core and absurdly broad wings. It has a higher redshift because you can see these shifted, and you can actually see the nitrogen 5 line resolved here where you couldn't in the Markarian 509. Now, this is the whole spectrum. So this is the region in the galaxy that gives you interstellar absorption lines. The excuse me, the geocoronal line has been removed, and if it makes this really dramatic, the wing here of the carbon-4 line is about 60 angstroms, which means that it's about 15,000 kilometers per second full width zero intensity. And you can also see in this spectrum that there's this narrow central peak. It's not quite as obvious here. All of the rest, this stuff, is absorption in our galaxy. This is the carbon-2 line, the silicon-4 line, and the carbon-4 lines. Okay, now this is a quasar. This is 3C273, which you can, as I said, you can see it. In this case, this is Lyman alpha. So you see just how shifted this is, that this should be 200 angstroms to the left. And also the nitrogen 5 line is present. The silicon-4 is substantially weaker, and the carbon-4 is, again, very strong and with distinct wings. But in other words, this looks like a Seyfert 1. Okay? And again, another Seyfert 1, 7469 is bright enough that you should be able to see it. And in this case, it actually shows the carbon-4 with a very narrow core. And the extended spectrum, where you can really see the narrow line region. Then, last one, 4151, which shows a deep absorption locally in the galaxy. That's what you're seeing here. So this is the carbon-4 line, but it's embedded in a region which is sufficiently dense and sufficiently ionized that you're actually seeing absorption from it. This is a narrow line. This is the prototype of a Seyfert 2, NGC 1068. You see the lines are completely different. First of all, they're lower ionization. This is a low redshift, so this is the helium-2 4686. This is the intercombination lines of carbon and silicon, carbon-4, silicon-4, nitrogen-5, and you see how distinct these are. Okay, this is actually blended with the geocoronal line. Okay, this is what's meant by a narrow line. And then the comparison that Seyfert 1s, which show the broad wings, Seyfert 1.5, that's sort of intermediate, and then the narrow line and broad line radial galaxies, okay, which are essentially quasars. And then finally, some of the absorption lines that show up when you go to high resolution, that 4151 and 5548 are both Seyfert 1s. And against the broad line region, there are these multiple narrow line regions that are in absorption, that are seen against the central object. Now, this is where you come in, if you want, that line ratios can be used to distinguish among these types. That, again, because H2 regions come from stars, the radiation that's creating the ionization and emission spectrum is nowhere near as hard. And so you don't see the same lines. And H2 regions and H2 region type galaxies separate from the Seyfert galaxies. That you can see that very distinctly depending on which lines you're using. These have their own specific names. It's not important for the type of galaxy. The thing that is important is that liners are somewhere in between H2 regions and Seyferts, these actually look like planetary nebulae. Okay? And you can see that the Seyferts in these different ratios simply don't. Okay, so now hoping that I can get the bloody whiteboard to work. I'm not sure it will, but we can hope. Um, okay, it looks like once again technology is failing us. So I'm going to try just one more. So if this doesn't work, okay, I'm going to have to do this. I'm sorry, the primitive way. So stop sharing, and I'm going to have to start. I need to be able to let my camera work. So can you allow that, Francois?
I need to be able to let my camera work.
Yeah, I need
Your camera.
yeah,
Okay.
I need video.
Ce que j'ai fait. Sorry.
I don't think we have to worry about YouTube sponsorship.
I apologize. Comment ça marche ça?
Nope.
In fact, if I understand, nobody
Okay.
can.
Well, just then to
Does it work?
okay.
Okay, I don't know what I did.
Okay, but
I propose continue and
yeah, let's
I
just do it
look.
this way.
I
No,
add to Google.
okay. Whatever, we can do this as one share and I can use this. Okay, so you can this is just a cartoon that I did while we were waiting. This should, I hope, explain what's going on to the extent that afterward we can go to the individual regions. But the point of the okay, what we mean by the inner broadline region is to say that there is a massive central object. Let's just call it what it is, a massive central black hole. Okay? And the nucleus is 10 to the 7 in our galaxy. It's a little bit less than that. To 10 to the 9, a little in M87, it's a little more than that. Central object, which is accreting. The accretion is from just about anything that happens to fall in. So within time, it's created around itself a general environment, which is a fairly dense circulating disk. That's very compact. Now, in this I don't have to tell you what's going on because we've already discussed this for novae and for cataclysmics. It's the same thing. It's just scaled up and the source is different. But you could think of this as what you would have if you put a black hole in a symbiotic. In fact, there are such things. They're called uh, BE X-ray sources, where you have a black hole or a neutron star orbiting in the wind of an O star instead of the wind of a red giant. But it's basically the same thing. You've got a disk here that's dense enough, heated enough, viscous enough that you see all of the same spectrum that you get from the accretion disks around white dwarfs and neutron stars. Okay, it's just a question of scale. Now, because it is, we have a little problem. Um, okay, so
Why?
it looks
Oh, okay.
okay. So we can do now the combination of two things. One is to have this and the other. Okay, so the so to make this point that when we're looking here at an environment that's on a scale larger than the one I drawn in this cartoon. Can you all see this now?
Uh, this is not
Okay.
accurate.
Let me wait.
Change the
We'll stay
position.
with the shared screen here.
Okay.
Okay, so this region is within a parsec, much within a parsec. And the region separates into two structures which are the same as we see in cataclysmics. That you have the accretion disk that gets to temperatures of 10 to the 7 or 10 to the 8 Kelvin, which means thermalized material, very, very, very hot, and also surrounded by a halo of electrons that may be evaporating off the disk. Then the region that in 1068 turned out to be the most important discovery that unified these objects was that in spectroscopy, using spectropolarimetry, the broad line region showed up. And this is very important that NGC 1068, I said, was a Seifert 2. That is, the broad lines, sorry, the permitted lines and the forbidden lines were both narrow. But looked at in spectropolarimetry, it was clear that what was going on was that the nucleus was actually partially hidden by dust and gas, but mainly dust. And the emission lines showed up in polarization because of scattered light. This was Antonucci and company in the mid-1980s. This changed everything. It meant that the only difference between all of these classes was the extent to which this surrounding donut was hiding the central object. And that if you look directly down into it, if you have a radio jet, that was a BLAC object. That's a blazar. That's why you don't see the emission lines. You're looking into this outflow, which is so concentrated, so accelerated, and so energetic that it just blinds you. It's like a deer in the headlights. If you're at a slight angle, you see the jet still because of the synchrotron, and you start to see a little bit of the emission from the galaxy. So this was the quasars were in this intermediate range where you could see into the central object. X-rays could penetrate the dust. This is one of the most important features I have to add, that in the same way that you can tell something about your innards by getting an X-ray. You can tell something about the innards of an active galaxy by getting an X-ray, because the dust, the organic material of the dust, is actually very, very transparent. So we can see the X-ray emission from sources in the galactic center where we couldn't, if we tried, identify these optically, because they're behind tens of magnitudes of extinction. And the same thing here. You might not be able to see the UV or the optical from the center, but you could sure as hell see the millimeter and also the X-rays. And that was the reason, or is the reason, why X-ray emission is the key to understanding the AGNs. That it is not dependent on the orientation. In the so-called unified model, this is an AGN. That now you see the narrow line region is everything out here. The broad line region is everything inside, and the broad line can be obscured, but the narrow lines will not be. And so when you have a starburst, that's because whatever you've got in the center is surrounded by regions of star formation. And we know that those exist because the galactic center shows it. That is, within the inner roughly 100 parsecs of the galaxy, there is an extended zone of star formation and molecular clouds and molecular gas, the so-called central molecular zone. There are several very massive clusters, including Arches and Pistil, which have stars that are on the very massive range. So these are regions that have formed stars very recently. There are supernova remnants throughout the region. There's heated gas throughout the region from diffuse thermal emission. So what we see in the galactic center is what goes on inside one of these, even if the central black hole is either barely accreting or in the kind of miserable little state that ours is, of like a couple times 10 to the 6 solar masses. In the really extreme cases where you have accretion onto an extremely massive hole like M87, then the extraction of energy from the hole, the extraction of angular momentum, and the combination of magnetic fields and circulation throws material out along the axis. And that's what creates the radio jets. Why they can maintain their integrity for such distances is not our problem, because from that point at which they exit the core of the galaxy on, we don't see them in the optical at all. There is some emission in the case of some of these lobes of gas from the halo. And we know that there's a circumgalaxy medium. These are all embedded in clusters. So there's some shock that's slamming into this background, but the details are yet to be worked out. The thing that you can see, on the other hand, is what's going on in the center itself, which is the effect of having this illuminating source relative to the background. This illuminating source, which is compact and not stellar. Now, why you care about the fact that it's not stellar is something I really need to explain. And the only way to do that is to go back to this little squib of a diagram. This is basically the problem of having a truck and a motorcycle in collision. That if you have a really slow-moving truck and you have a motorcycle that scatters off of it, the likelihood is, if the motorcycle is coming into the truck, that when it's scattered, it's going to come out with more energy than it went in, okay? Because it's going to get accelerated in that collision. On the other hand, if you have the truck hitting the motorcycle, the truck is uh, not really going to do very much. It'll get a little bit of acceleration, but the motorcycle may very well lose all of its energy. To put it much more bluntly, if you've got an energetic electron that scatters light, it if the light has an energy lower than the electron loses energy, or sorry, if the let me back up. If the photon energy is lower than that of the electron in the collision loses energy and the photon comes out at higher energy. In other words, higher frequency. If the if this is relativistic, which is what you'll have if you have radio emission, then the photons that are emitted, and this is the part that will sound weird, but the radiation emitted by these electrons in their spiraling can scatter not on the identical electrons, which doesn't matter anyway, but it can scatter on the other electrons that are in the same region. And in that process, the electrons lose energy and the photons gain energy and gain massively. So instead of being of order hundredths of an electron volt or even thousandths of an electron volt, they come out at gigavolt energies. And so in that case, which is called synchrotron self-Compton, the electrons that are emitting are also the same population that can scatter the radiation from all of the other electrons. The result is you get light from the galactic nucleus, from this very compact region, which is because it was emitting at very low frequencies. So you don't see necessarily strong radio because that's been converted. You see gamma ray. And that is what you see in blazars and quasars. That's what you see with the Cherenkov array telescopes that go up to a TeV, and routinely with Chandra at KeV, and with XMM and integral at MeV, and ultimately with Fermi going up to GeV. So you cover this whole hard part of the spectrum, which is completely non-thermal. The only reason it's there is because in this surrounding region and from the jet, the energy of the photons that are emitted by this torus and by the disk can simply be scattered. This is the remarkable part of this, is that this is probing a region which is in the broadline region. So if you are looking at the variations of the emission lines from the broadline region, you're actually probing what's going on with the base of this radio source. Now comes the part that links everything that we've been talking about in this set of discussions. Remember when I was mentioning light echoes in mergers, in supernovae, that if you've got a bright source that goes poof, then over time you can get the scattering and emission from the region around it. Okay? I want to make sure that this is not a bad memory. Yes? Silence. Okay, so I'll assume that you all remember this. Um, the basic argument was that if you have a source that goes off, then in time, you here will see light that's coming from different regions, all of which were illuminated at the same moment, but arrive at your place at different times. Okay? You got it? So if we go back to the cartoon here,
Good.
okay, so if we have in this disk radiation because the central object burps, it hiccups, it doesn't feel right. In other words, you have a pulse. That pulse may be ionizing. And this is the part that is exactly the same as a nova, that this region will be illuminated at a time that's different than this and different than this. And because the galactic nucleus is covering a region that may be light years in size, the light travel time from the central object to these regions will be slow enough that you may be able to resolve it. Now, what happens is the same as with a nova. If the central object varies, you can think of these as the ejecta. This region is ionized and recombines differently than this region and this region and this region. The difference is this is circulating. In a nova, it's expanding, but it's the same thing. The line profile changes. So what you would expect if you had Keplerian motion is the inner part should have a different orbital velocity, higher than the outer part. So the broad line wing, which is coming from the inner part, is going to be affected by the central object before the narrow line region. Okay? This is called reverberation. It's the same damn thing as an ionizing light echo. It's exactly what we see in novae, that if you have a central pulse and it's reprocessed by lines in a dynamical environment, different parts of the line will change at different times because you're seeing the emission from different regions with different velocities at different times. The amazing thing is that those who those who created the picture that I've spent the whole last session on, that is this last hour and a half, all thought only in time independent terms. As I had said when we talked about light echoes, if you've got a spherical region, nothing changes. All you see is a change in the intensity of the line. You don't see changes in the line structure. If you've got a dynamical field, you see those changes. But the people who created the paradigm for the Seyfert galaxies and for quasars were not those who were used to looking at objects that were transients. And those who do transients don't look at Seyfert galaxies. So the result is you have people describing the same phenomenon, thinking that they're somehow different, where they're not. Perhaps the best example I can show you is here. If I can open the damn thing, open with here. So I'm going to go now to a different screen. Okay.
Yes.
This is Novacast. It's a paper that we've done, and by we I mean also with Francois and with ARAS. This is actually the ARAS data, which is why I'm showing you this. This is a nova. It's a slow nova. Never mind what the details are. It's simply that here you're looking at the variation of what would be the narrow line region, except this is ejecta. You'll notice that, leaving aside the helium-2 line that's on the right, on the left, look at this line, okay? That It first shows an asymmetry going toward the blue, toward the red, then it's flat, then it shows the asymmetry in the opposite direction. Okay, here it's asymmetric to the blue, flat, red, flat, blue. Okay, this is a central object illuminating ejecta. The ejecta have a velocity field, and the velocity is confined, you can see that from the helium, to 2,000 kilometers per second. And the helium line changes. You see that the core changes relative to the wing? Okay, this is the same thing. You have an illuminating central object that's causing the ionization and recombination to proceed differently in different portions of the environment. If this were an accretion disk, it would be the same thing. If it were the circumstellar medium, it would be the same thing. Okay? The difference in the case of the active galaxy is that this is bound. So the remarkable effect is that because you know the time delay between the changes in different portions of the profile, you can say that there's a propagation of the pulse that happens at the speed of light. And so by looking at where the line is changing, you're actually mapping out the structure of the region around the hole. The parts that will vary first are the highest velocity. The parts that vary later are going to be the lower velocity. So you can reconstruct the gradient in the velocity, and from that, you can determine independently the mass of the central hole. And that has been done now for dozens of galaxies. It's a very difficult process because it involves coordinating different observatories, and the timescales require pretty much continuous observations. But it has been done successfully, and it agrees with what I'm talking about, that the broadline region, which is the part for which this reverberation mapping is done, really is compact and really is circulating with essentially ordinary orbital motion around an object whose mass is considerably, in general, considerably larger than the mass of the object at our galactic center. Now, what this all means is that because these objects are in galaxies, they're faint. The interpretation of the spectrum in your experience using a slit spectrograph with a wide slit, so you can get the emission lines, is going to have the problem of contamination from a galaxy spectrum, with the exception of the quasars, where you don't have to worry about the background galaxies because the nucleus is so relatively bright. In 1068 or 4151 or 5548 or 7469, the ones that you can easily observe in both hemispheres, the wider the slit, the more galaxy contamination you're going to have. It's not important just to get a feel for what these lines look like, but if you're going to do anything quantitative, you have to be careful to remember that you're not just seeing a point source. This is the same thing as looking at the spectrum of a star in another galaxy, that you're always going to have contamination. In the LMC, for example, if you're looking at a single bright star, 1 arc second is only about a parsec. So the likelihood that you're going to have another bright star in the same slit is relatively small. But here you're looking at maybe 100 parsecs, where it's virtually certain that you have other stars in the field, not just the background from the galaxy, and not just the central hole. where all of this sort of comes together is, so let me stop the screen share for a moment. Um, so you can also see variations photometrically in these. This is the basis of the reverberation mapping. Variation in the ultraviolet at about 2300 angstroms, and then variation from Swift that shows if you close your eyes and cross your fingers, you can sort of believe that this is showing the same sort of curve. And the part that's important is this is the variation of a type 1 Seyfert. And it is kind of sort of periodic. Uh, there are some that are much active galaxies that are even more periodic than this. I just want to show you that this is what is going to show up in the reverberation maps. The problem with those, unlike novae, with a nova or a supernova, you know exactly when the bugger went off. Okay, it's a single event. If you've got something like this that's going up and down over time, you've got the difficulty of knowing if you see a light echo, if you see a reverberation. You have the problem of knowing which of the parts of the cycle and which cycle was responsible. It's much more difficult to work through. If you have an impulsive event, which is why supernovae are so important for light echoes, you can always go backward in time, but you can't necessarily in something like this. But this is characteristic of what's going on. Within 50 light, it's within 50 light days of the center. And so quite clearly, this is not an ordinary cluster. Okay, this is actually variation of the central object. More to the point, the amplitude here is enormous. It's 10% in the UV. And in the X-rays, it's even larger, even though it's all over the place. This is not error. This is actually the variation of the X-rays. And it's on timescales of literally days or tens of days. So here you're really seeing the variations of the central engine. Um, so as a so um, this is actually a good point because I've really tried your patience to stop. Um, and I have to stop with this photo. Um, this was Ricky. Some of you knew him. Um, Ricky died today, and it was because we had been to Haute-Provence and with you over the years that I wanted not only to continue, but also to remind you that the that you're all very much a part of the family. Um, this this was from our last trip to OHP. It's here, and I hope you take an inspiration from that view. That there's always something beyond the horizon. So I'll stop there and hope there are
Oh,
questions.
our deep sympathy from all, Steve.
Thank you. Um, thank you.
Thank you.
The thing that's important is what we're doing now. That's you know that's what continues, and that we've now reached the end of the season, and I hope you'll want to continue in the fall. There are lots of other things we can discuss if you'd like to. Um, I just want to thank you for these months. They are very precious to me, and I hope I haven't done too much damage. Um,
No, not at all. You know that all your thoughts are very appreciated. We have had almost 200 registers, in fact, and each session between 20 for this one to 40, 50 people, and also many watchers to the video recorded in YouTube with the participation of many amateurs, of course, but also doctorants, postdoc, and even
yeah.
astronomers and so on. Yes, very appreciated. Thank you very much. And of course, if there is a special event during the summer, we
Oh,
can
well,
uh, we can
I'll be here.
schedule. You see what I mean?
Oh well,
Eventually, Nova event.
you're talking chicken entrails again.
Perhaps.
Um, so yeah,
Oh.
um, yeah, right. Well, as long as it's not behind the sun, um, that which we have been anticipating for an absurd amount of time may actually happen someday. So yes, um, but there's an interesting nova now in the southern hemisphere that has all of the earmarks of being absolutely ordinary and consequently being relatively bright, worth following. The one thing that's especially interesting right now is that there are some remarkable similarities with what we see in transients, like mergers at the early stages, and the sodium line being extremely fragmented and showing velocities of like 300 kilometers per second and an incredible optical depth in the calcium resonance lines, so the H and K line. What I suggest if anyone wants to follow this bugger, because it's very low for the northern hemisphere, is try to push out as far into the red as possible because it's very important to get the calcium two lines at the triplet, so at about 85 to 8600 angstroms, and also the oxygen one line at, excuse me, at 8446, because those are both important probes of the density of the ejecta. And it's not that this is going to be spectacular, it's that every time we have these early stage spectra, what happens in the literature is people take an initial spectrum, they identify what it is, and then they say, well, now we know what it is, who cares? They go away and do something else. So there's a real dearth of physical data on these early stages, which is when some of the most interesting processes are going on, where we actually see the structure of the ejecta sort of peeling through as it becomes first thick and then thin. So we can get information about the ejecta, about the explosion, that we can then apply from lessons learned to a very wide range of other objects. If there's anything that I hope you can take away from all of our discussions, it's that while individual sources or classes of objects may be fascinating, they're only ultimately physically important because they are pieces of a bigger picture. And that what I was trying to say today and what I've been trying to get across in all of our discussions is that when we change the scale or when we change the mix of physical processes, we're still using the same basic mix. It's just weighted differently in different classes of objects. So what we learn from the study of the individual classes of events is the way that things look when you have a specific arrangement. Then you figure out which processes produce what by doing the comparison between these different classes. And ultimately, this gives you the tools to analyze any of these objects when they happen, instead of simply saying A looks like B, so it must be B, which is the way that machine learning works. That when you do taxonomy, when you do a library and say, this particular first spectrum looks like, let's say, 1997 IJX, and consequently, it is that class of transient or supernova, that's garbage. You've identified what it looks like. Somebody may look like Emmanuel Macron, but that doesn't mean they're him.
We said no politics, my dear.
Well, I had to throw friend. That's not politics, okay? I didn't say anything about his comparison with anybody. But if somebody walks down the street and you say, I've seen this person before, and of course you haven't, what you're doing in your head is a pattern match, which is exactly the same thing that happens in machine learning. On the other hand, so you've learned absolutely bloody nothing, except that you had somebody cross a threshold for similarity. Okay? Now, if on the other hand, you have a time series and you say, we know objects that in their time series have shown this behavior. That's physics, because now you have dynamics. Now you have not just a snapshot, but you have development. So you can look at a person, for example, as they age. You can take photographs of them at different ages and say, well, this person is developing in a certain way by using that comparison because you have a time series to work with now. Okay? And it's exactly the same thing when you're using this to identify transients. And when you're ultimately doing the identification of physical processes, even in objects that don't change. In the broad line versus narrow line region of active galaxies, it's the broad line region that changes, the narrow line region doesn't. But the way you know that there must be a narrow line region is because there are certain physical processes that can't happen if the densities are too high. So you can use that information and then also take time series to know what's going on. Okay, that's the bottom line of everything we've been doing for this whole sequence. That persistence is something important because put it bluntly, nature runs the experiment without telling you when it's going to start, when it's going to end, or where it's going to happen. But once it's started, it runs its course. Then you can figure that out by understanding the way that things change. And that's the bottom line for everything we've done. So again, thanks. And have a very good summer all.
Thank you very much. I've
Thank
enjoyed
you.
that.
Yes,
Thank you, Steve.
excellent, sir.
Thank you, Steve.
Thank you very much,
So
Steve.
hugely inspiring.
Okay. Goodbye all.
Goodbye.
Goodbye.
Goodbye. Have a
Goodbye.
good summer.
Mm.